and welcome back to the chapter on residence time distribution. We learned in the previous videos how to define the RTD and what an ideal distribution function looks like for different ideal process units. Now we look at RTD measurements. The residence time distribution is usually measured with a tracer. The mathematical equations represent the response to either a step change or an impulse input. And this is also how we measure the residence time distribution. In order to be able to obtain a measurement, we need to cause a change in the composition of the material that we measure at the outlet. The material that we add in order to change the composition of the bulk is called a tracer. If we add this, we need to be careful because any addition of material or change of composition can disrupt the flow pattern in the equipment and lead to an incorrect measurement at the outlet. This leads to the next question: what problems can be caused by a tracer? We in the group here have already seen cases in which the addition of a tracer made a formerly very cohesive material relatively free-flowing. This changed the flow pattern completely, which can happen if the bulk material interacts with the tracer, such as reducing the cohesive forces between particles. Even if the tracer does not change the flow pattern, it could still have a different flow pattern. For example, this can be the case when the tracer has a very small particle size compared with the bulk and tends to aggregate in corners or on the wall of the equipment. This would lead to long tailing, which then might not be true for your larger particles in the bulk. But even if the tracer has the same size and does not change the performance of your material, there is still the possibility you will see the wrong result. Another example we observed in the group was when the bulk material had a moisture of around 10%, so very moist. This was an intermediate product for continuous drying. The tracer we added was very soluble in water. Unfortunately, what was not considered was that the moisture in the bulk was enough to dissolve some of the tracer. Instead of being transported only by the particle flow, the tracer was also transported via diffusion in the particles themselves and the particle bed. This resulted in a completely different flow pattern and very long tailing. Once we saw this effect, we immediately realized that we needed to change the tracer. So the ideal properties of a tracer would be: it has the same flow characteristic as your bulk, the same material properties, and it does not interact with your bulk. But still, it has one feature that is distinctly different, and the chosen detection method should have a high sensitivity to that specific feature of the tracer. Depending on the circumstance, different tracer materials can be of advantage. Let's now look at the options for tracer addition. In general, there are two options when adding a tracer to a system. Option 1, you conduct a step change experiment, or option 2, an impulse test, where you simply add the tracer. If you carry out a step change experiment, you either change all material in one step or you change just one material. Practically, it looks like this. You could have, for example, 3 feeders in your production line. All of them are filled with different substances from your formulation. When you conduct a step experiment, you would switch one material from one feeder with a tracer substance. The inlet concentration of the tracer should look like this. The cumulative distribution function would then show you when you have reached the maximum concentration of the substance in your bed at the outlet. The second option is that instead of still feeding 3 materials, you would change to one single substance that would substitute for all 3 substances and act as a tracer. You can imagine that such a drastic change in material can easily lead to a change in the flow pattern. Therefore, a derivative of this step change is to just change the ratio of one substance. For example, change the API concentration from 30% to 50%. This sounds nicer, right? But still, this option has its challenges. Later, when we talk about the function of the different equipment, you will understand it better. But let me briefly outline the issue now. The mass flow rate of the feeder is very hard to adjust. If you change the mass flow rate from 30% to 50%, it can take several minutes to reach the correct set point. So you will not see a sharp change, which is required for a step change experiment. If you change one material, there is also another option. If you are running normally with 3 feeders, but you have 4 available, the single material step change can be achieved by simply turning off one feeder and starting with the 4th containing the tracer. Again, in this scenario, it would take the feeder several minutes to reach the correct mass flow, but you could trick the system. You could let the feeder with the tracer run, but discard the material. Then, when the step change is carried out, you would turn off the original feeder and stop discarding the tracer material. This could be a little hard to grasp. Therefore, we prepared an animation for you. Here you see the feeders are running, the material being discarded, and then, at once, the tracer goes into the system. The corresponding response function is the cumulative distribution function f of t. You see that here in this graph. I depicted the curves for the blender, granulator and tablet press. Depending on the mixing in the equipment, stagnant flow zones, etc., you get different shapes for these curves. The detection method for the tracer is different depending on the substance you use. Typically would be to use an NIR probe, which is a near-infrared spectroscopy. It is installed as a pad tool in your system. To do this, you would need a substance that does not overlay with the response signal from your bulk. If you use the API as a tracer and change the concentration, it would also have the advantage of using the calibrations you need for this test, also for the production process. Advantages of the step change experiment are: the test can be carried out using the automation system without manual interference. You can use material concentrations that are within the calibration space of your PAT tools. And you have lower risk for secondary disturbances due to material property differences. The disadvantages are: the step change may be hard to carry out with the available hardware you have. It is challenging to keep the mass flow constant, as I mentioned. And the measurable effect of the response function can be lower. The other option to determine the residence time is to conduct a pulse experiment or tracer experiment. In order to do that, you would manually introduce a small amount of tracer substance at a set position in your production plant. In this example case, I show here, we introduce the tracer before the blender. During this tracer addition, it is essential to add only a small amount that does not significantly increase the mass flow rate, but on the other hand, provides a strong signal for the detection of the response. Depending on the detection method, different tracers are used. Sometimes it may be the easiest to use a color. This means that you use existing material from your formulation that has been dyed with a different color, or you add a different material with a different color. You would then evaluate the response function with a camera, or you could also analyze samples offline. This offline process can be conducted either by taking pictures or with an analytical method. UV-Vis is very useful in this case. Another possibility is to analyze the powder stream online with an NIR, similar to the step change approach that I mentioned before. Usually, this type of detection method is more effort because you have to create a chemometric calibration model for your tracer at different concentrations. And since the NIR probe is often sensitive to the placement position, this can be tricky. You would need to carry out tracer runs in the plant with a known tracer composition to calibrate the model. which would ideally mean you process a blend containing a constant tracer composition. This is obviously a lot of effort for different concentrations. So the preferred option is to carry out an offline calibration with different amounts of tracer in the bulk sample. The impulse response function is E of t, which you see in this graph. Similar to the step change response, you can observe different system dynamics for the different unit operations. The advantages of the impulse or tracer experiment are: you only have a small change of the composition. Therefore, you have a lower risk for flow property changes. The range of the tracer concentration in the bulk is smaller than for the step change experiment. This might be very relevant if the measured signal change is not linear to the concentration over the complete measurement range. Disadvantages of the impulse test are: the tracer addition can often only be carried out manually. There is the risk of process disruption due to the human interference. And it can be challenging to find a suitable tracer material. To give you an impression of how such an experiment would look like, we created a short video that guides you through the process of a color tracer experiment on a continuous twin screw extruder. So make sure to watch that. With that, I'd like to thank you for your attention. I hope you are enjoying this course. Please provide us with feedback. We are always excited to hear what you have to say, which will provide us with the opportunity to improve.